Okay? All right. Compute the value of K for the Earth. What is the value of K we just talked about? Is 4 pi squared over G-ms, G times the mass of the Earth. And that is the value for K for the Earth, K for Venus, K for Jupiter, K for Mars, K for Mercury, all the other planets. The value of K will be the same for all planets in the solar system because it depends only on the mass of the Sun. If T is the T for Earth, what is the period of Earth? The period of Earth is 365 days. And R, the mean distance of Earth from the Sun, it is actually a constant value which is used very often in astronomy. It is called an astronomical unit. The distance, the mean distance of the Earth from the Sun is 150 million kilometers. That is 1.5 times 10 to the 11 meters. This is the average distance of the Earth from the Sun. So, we know the period of the Earth, we know the average distance of the Earth from the Sun. So, can you calculate K for Earth? So, you can calculate it from this equation right away. We know that the square of the period equal to K times the cube of the average distance of the planet. Is that right? This is the statement of the third law. T squared equal to K R cube. We know the period of the Earth. We know the average distance of the Earth from the Sun. Therefore, K equal to T squared divided by R cube. All right. K equal to T squared divided by R cube. This is the period, 365 days, converted to hours and seconds, and then square it, divided by R cube. R is 1.5 times 10 to the 11. Alright, calculate that on your calculator and see whether you get this. 3 times 10 to the negative 19 seconds squared per meter, and that is the value of K for the Earth. Once you calculate the value for K for the Earth, you know that this is the same value for Mars and so on. Well, you notice that we calculated K using this equation. K equal to T squared over R cube. But do you remember the quantity K is actually 4 pi squared over G-ms. This is the quantity we call the K. Since we calculated the value of K, and since we know the value of the universal gravitational constant, we can now find the mass of the Sun. You see that? Without going anywhere near the Sun, we can now calculate the mass of the Sun from here. I'm going to ask you to do that on your own. And let me know. If you can send it to me, I will appreciate that. Calculate a value for the mass of the Sun using the value of K we calculated for Earth. Okay, let's move on. And that is the value of K. Let's do a small problem. Venus has a rotational period of 243 days. What would be the altitude of a SYNCHRON satellite for this planet? Mass of Venus is 0.815 times the mass of the Earth. What is a SYNCHRON satellite? You know that we depend a lot on satellites for our communications. If you have a communication satellite, you want to station that satellite always above a certain point on the surface of the Earth. If there is no synchronization between the rotation of the Earth and the rotation of the satellite, then the position of the satellite will keep on changing as the Earth rotates. That means if you send out a communication satellite, it has to be synchronized. The period of that satellite needs to be synchronized with the period of rotation of the Earth, so that the satellite can be found always above a certain point on the surface of the Earth. Such a satellite is called the SYNCOM satellite. Now here we are talking about a SYNCOM satellite for Venus. A SYNCOM satellite has the same period as the period of rotation of the planet. Is that right? The satellite must have the same period as the period of rotation of the planet. Now the period of the satellite is 243 days. That is the period of Venus's satellite. We are looking for R, the mean distance of the satellite from Venus. Now here, don't confuse here, this is not the solar system. This is Venus and its satellite. You see, earlier we had the planets going around the sun. In that case, we found K is 4 pi divided by G times the mass of sun. But this time, we have a satellite going around Venus. Therefore, the value of K for this situation is 4 pi squared divided by G times the mass of Venus. So don't confuse here, very important to know that. So we got T squared equal to K times R cube, the square of the period of the satellite, equal to K times the cube of its average distance from the planet. And the satellite is the satellite for Venus. Therefore, you notice here, in place of the mass of the sun, I use the mass of Venus. And the mass of Venus is given to be 0.815 times the mass of the Earth. And so, we need to find what would be the altitude of the SYNCOM satellite. We need to find this R. So, if T squared equal to 4 pi squared GM Venus times R cube, therefore R equal to cube root of T squared G mass of Venus divided by 4 pi squared. I'm sure you understand that. R cube equal to T squared times GM Venus divided by 4 pi squared. R equal to cube root of that quantity. Now that will be now T squared G times the mass of Venus is 0.815 times the mass of the Earth divided by 4 pi squared. And I have given you the mass of the Earth some time ago. So that will be T squared, the square of the period of the satellite, 243 days. Convert that to seconds. Times G, 6.7 times 10 to the negative 11. Times 0.815 times the mass of the Earth is 5.98 times 10 to the 24 over 4 pi squared. You can see in this particular part of the course, you have a lot of these slightly complicated calculations, and you must feel comfortable using this on your calculator. Okay? And that gives you 1.54 times 10 to the power of 9. If you don't know how to do this on the calculator, well, you can do them piece by piece. In other words, you can do all this quantity then divide that by 4 pi squared to get you that quantity. And to take the cube root, how do you take the cube root of a quantity on the calculator? Raise it to the power 1/3. That is how you find the cube root. Once you find this number inside the radical sign, raise it to the power 1/3. Okay. Let's do another one.